Today, we are plunging headfirst into, well, the incredibly ambitious quest for fusion energy.
Yeah, that's sort of holy grail, right? Mimicking the sun for clean, limitless power.
Exactly. And it's not just science fiction anymore. It's a real global race happening right now, and we want to unpack the strategies of the key players involved.
Absolutely. So for this deep dive, we're zoning in on Europe's plan. It's all laid out in the European Research Roadmap to the Realization of Fusion Energy, the Eurofusion Roadmap.
Right. A big document. And we'll contrast that with what's happening in China, which seems to be moving incredibly fast.
Yeah, we're drawing on that roadmap itself,
Yeah.
plus some really good reports from places like Nature.com, Asia Times, and even some chatter on Reddit, actually.
Okay, great. And this matters to you listening because it's fundamentally about the future of energy. It underpins everything, tech progress, global influence.
Mm-hmm. You'll definitely have some aha moments when you hear about the sheer scale and the, frankly, quite different ways Europe and China are tackling this fusion challenge.
So the Eurofusion roadmap, that's Europe's strategic blueprint.
Yep. And the articles and discussions give us a window into China's speed and investment, and also how the U.S. is kind of looking at this whole competition.
Got it. So our mission, as always, is to pull out the key strategies, the timelines, as much as we know them, and the big challenges Europe and China are facing.
Basically giving you a clear picture of this really high-stakes global race for fusion.
All right, let's dive in. Europe's roadmap first. It's not brand new, is it?
No, not entirely. The first version came out back in 2012.
Yeah.
This update, from September 2018, it basically keeps the same overall goal, getting electricity from fusion.
Still the main objective.
Yeah, it's been super important for getting everyone in Europe pulling in the same direction, research-wise.
Okay, and the roadmap must talk a lot about specific facilities. I know ITER is a big one.
Oh, huge. ITER and DEMO are absolutely central. ITER's being built in France right now,
Right, the international project.
Exactly. Its job is basically the big science experiment, prove you can get a sustained burning plasma that makes more energy than you put in.
The Q1 goal.
Precisely.
Mm-hmm.
And European labs are all geared up to, really exploit the results from ITER once it's running. Then comes DEMO.
DEMO, that's the demonstration power
Yeah,
plant.
that's the one. It's planned as the next step, the prototype for an actual commercial fusion power plant that would, hook up to the grid.
So ITER proves the science, DEMO proves the technology for a power station.
You got it. And other facilities like JET in the UK, well, until recently, and JT60SA in Japan, they're crucial stepping stones preparing for ITER operations. Plus, the Wendelstein 7 accelerator in Germany adds another angle.
Okay, so what's the timeline looking like for DEMO? It sounds like it's still quite a way off.
It is. The roadmap suggests maybe having early conceptual designs for DEMO around 2027.
Yeah.
But the decision to actually build it, that's probably a few years after ITER shows it can run high-performance deuterium-tritium plasmas.
When it's really fusing fuel properly?
Right. And after we get the first results from these things called test blanket modules, or TBMs, inside ITER,
TBMs, test blankets, what are those for?
they're designed to test how we can actually breed tritium fuel inside the reactor itself using lithium. Super critical for future plants.
Ah, self-sufficiency. Got it. So when might DEMO actually be operational?
The estimate is roughly 20 years after ITER demonstrates that high-power burning plasma. So yeah, we're likely looking well into the second half of this century.
Okay, long road ahead. And the roadmap must lay out the major hurdles, the big challenges.
Oh, definitely. It breaks them down into specific missions. Mission 1 is about plasma regimes, how to control that super hot plasma.
Keeping it stable.
Exactly. Mission 2 is plasma exhaust, dealing with the immense heat and particles coming out, a huge engineering problem.
Yeah, I can imagine.
Mission 3 is materials, finding stuff that can survive the intense heat and neutron bombardment for years.
Right, the radiation damage.
And Mission 4 is that tritium self-sufficiency we just mentioned, making its own fuel, absolutely essential.
Makes sense. The roadmap also talks about balancing innovation with pragmatism. How does that work?
Yeah, it's interesting. They acknowledge DEMO needs innovation, no doubt.
Mm-hmm.
But for the first iteration, they're suggesting a more pragmatic approach.
Meaning?
Meaning using technologies and operating methods that are reasonably well understood, things they can hopefully extrapolate from ITER with some confidence.
So don't try to do everything brand new all at once for the first DEMO.
Kind of. Get the basics working reliably first, using materials they think can handle the initial neutron exposure. But, and this is important, they also stress exploring other DEMO designs in parallel.
Ah, keeping options open.
Exactly. And getting industry involved right from the get-go. That's seen as vital for, manufacturability, supply chain safety, all that practical stuff.
And ITER's role isn't just the science, it's also testing hardware for demo, like those TBMs.
Precisely. ITER is the only place to test those tritium breeding components in a real high-power fusion environment before you commit to a demo design.
So the TBM results directly feed into demo choices.
Absolutely. The roadmap makes it clear. The demo blanket design work and the European part of the ITER TBM program need to be tightly linked, testing different coolants, breeder materials, the works.
It really paints a picture of very interconnected long-term plan.
It does. And it's not happening in a vacuum. The roadmap mentions links to other big science projects, like the European Spallation Source,
Okay.
advances in computing for handling massive data, material science crossover with next-gen fission reactors,
Yeah.
sophisticated remote handling tech.
Right, robotics for a radioactive environment.
Exactly. And sometimes you get these unexpected spin-offs, too.
Like what?
Well, the document mentions things like superconducting cables developed for fusion finding their way into MRI machines.
Oh, wow.
Yeah, or even an explosive forming technique used for the A380 cockpit, having roots in fusion research. Eurofusion actually promotes these spin-offs quite a bit.
That's fascinating. So the journey itself yields benefits. Who's actually managing all this in Europe?
Two main bodies. There's Fusion for Energy, or F4E. They handle Europe's contribution to building ITER and other big projects.
The hardware side.
Mostly. And then there's Eurofusion itself. That's a consortium of research institutes across Europe that manages the actual R&D program outlined in the roadmap.
Okay, F4E builds, Eurofusion researches. Got it. The roadmap also mentions a baseline architecture for demo.
Yeah, that's about creating a coherent, integrated plant concept.
Yeah.
Bringing all the subsystems, magnets, heating, cooling, tritium plant together in a single design framework.
A holistic view.
Right. A systems-oriented approach, they call it. Trying to tackle those integration challenges early on, figure out if the tech is really up to snuff.
And this design process happens in stages.
Yes, 3 main phases outlined. First, pre-conceptual design. They look at multiple concepts, assess them, and aim to narrow it down by around 2027.
Okay.
Then, conceptual design. Developing the chosen one or ones in more detail, maybe picking a single architecture by 2027, 2029.
And
Engineering design, that's the really detailed stuff. Prototyping, testing components. Construction might potentially start around 2040, but that really depends on ITER's success.
a lot hinges on ITER. And some big decisions need to be made relatively soon then.
Absolutely. Before they finish that conceptual design phase, they need to lock down key choices.
Such as?
Like the diverter configuration, that's the exhaust system. How to protect the first wall facing the plasma, which breeding blanket concept and coolant to use, the main plasma operating mode, the mix of heating systems, critical choices.
And cost must be a huge factor. Mission 7 you mentioned.
Right. Competitive cost of electricity is the goal. That means looking at everything, lowering manufacturing costs for components, maybe using advanced manufacturing.
3D printing parts for a fusion reactor.
Potentially. Also, increasing availability, making sure the plant runs more often. That means better remote maintenance, quicker repairs, and thinking about how fusion fits into the whole grid with renewables.
Let's circle back to a couple of those huge challenges. Plasma, exhaust the diverter.
Yeah, that's a massive one. They're working on a baseline design, but also exploring alternatives. Things like different magnetic shapes, double null, snowflake, super X diverters.
Trying different ways to spread the heat.
Essentially, yes. And even looking at using liquid metals as the target surfaces because they might handle the heat better. They hope to pick a concept in the early 2020s. Well, we're past that now, so that decision must be evolving.
And maybe tested in that Italian facility, IDTT.
Exactly. The diverter test tokamak in Italy could be a key test bed if an alternative looks really promising.
And tritium self-sufficiency mission 4. You said ITER is the first real test.
Yeah, it's absolutely non-negotiable for demo and commercial plants. ITER's PBMs are the first chance to see how well these breeding blanket concepts actually work in practice, making tritium from lithium under real fusion conditions.
So much depends on those TBM results. And materials, mission 3.
Crucial. They're focusing on special steels like ferritic martensitic steels for the main structure, materials for high heat flux areas, functional materials for breeding tritium, stopping it from leaking.
A whole range of specialized materials.
Right. And a big issue is we don't have decades of data on how these materials hold up under intense, long-term neutron bombardment, like they'll see in demo.
So how do they predict that?
A lot of advanced computer modeling and simulation, alongside tests and specialized materials, irradiation facilities. It's a huge research area.
And you need people to do all this work. Training.
Definitely.
Mm.
The roadmap stresses supporting fusion education, PhD programs, things like Eurofusion researcher and engineering grants are key for training the next generation.
Building the workforce for ITER and DEMO.
And working with industry to make sure the training matches the skills needed.
Okay, one last bit on the roadmap. Enabling research. What's
Yeah.
that?
It's basically a program for smaller, potentially more innovative projects, things that might bring new ideas or techniques into the main missions.
More exploratory stuff.
Kind of. Could be fundamental science, could be novel tech ideas, computational tools, stuff selected for excellence and innovation potential that doesn't neatly fit into the big mission boxes.
Okay, that gives us a really solid picture of Europe's structured long-term approach. Now let's pivot to China. The report suggests things are moving very differently there.
Very differently and very fast. The scale of investment is the first thing that jumps out. Jean-Paul Allain from the US DOE suggested China might be spending around $1.5 billion a year on fusion.
Wow, $1.5 billion annually. How does that compare?
He estimated it was nearly double the US government's allocation at the time. And he stressed that the speed of their progress might be even more significant than the dollar amount.
That kind of funding allows them to do a lot, presumably.
It potentially allows them to pursue multiple approaches much more aggressively than, say, Europe is right now. Maybe try riskier things in parallel.
And it sounds like it's a top government priority.
Absolutely. Their current 5-year plan specifically flags building major fusion research facilities as key national science infrastructure. That's a strong signal.
Is their approach centralized, like Europe's focus on ITER DEMO, or is it broader?
It seems broader, actually. They have major government programs like this new China Fusion Corporation that was announced and a big new machine called BEST.
Best.
Yeah, we'll get to that. But alongside the government stuff, there's this really booming private fusion sector.
Yeah.
Companies like ENN, Startoris Fusion, Energy Singularity.
Private companies building fusion reactors in China.
Yeah, Energy Singularity is building a tokamak using high-temperature superconductors. Similar tech to what Commonwealth Fusion Systems is doing in the U.S. So it's this mix of state-led and private innovation.
Interesting dynamic. Tell us about BEST.
Okay, BEST stands for Burning Plasma Experimental Superconducting Tokamak. It's planned to be a big machine, ITER scale roughly, using low-temperature superconductors.
At its goal.
The big one, fusion break-even, getting more energy out than they put in to heat the plasma. It's under construction in Hefei, which is a major fusion hub in China.
So a major national project aimed at a key milestone. How open are they about all this work? International collaboration.
Well, the Asia Times piece noted Chinese scientists are very active internationally. They go to conferences, they share data, they learn from others.
Okay, so they're engaged.
They are. But the article also suggested some aspects of their programs, maybe the overall strategy or specific goals, are perhaps less transparent than, say, European or U.S. programs.
Like that China Fusion Corporation announcement.
Yeah, that seemed a bit unclear initially. So active participation, but maybe not full openness on all fronts.
Fascinating contrast. Okay, let's bring in the U.S. perspective. How is all this activity in Europe, and especially China, viewed from the States? Sounds like some concern.
Definitely concerned. The U.S. has plans, things like public-private partnerships, the NFUS program to boost innovation.
Right.
But the general feeling echoed in these articles is that the U.S. government funding levels are just too low to really compete effectively, especially against China's massive investment.
Not enough fuel in the tank, so to speak.
Pretty much. There's a worry the U.S. might fall behind in this critical technology race.
And what about people? There was that stark statistic about PhDs in the Asia Times piece.
Yeah, the estimate that China might have 10 times more fusion PhDs than the U.S., it sounds dramatic.
It does.
But Andrew Holland from the Fusion Industry Association, he had a slightly different take. He thinks the workforce will grow in the U.S. as the market demands it, especially with private companies hiring.
So not necessarily a lack of new talent being trained.
His bigger worry is actually retaining the top experienced talent within the U.S.
Brain drain.
Potentially. He worries that if U.S. government funding stays limited, the most senior researchers might be lured away to, say, the U.K. or Europe, or maybe even China, where there might be more resources and bigger projects.
So train them up and then risk losing them.
That's the concern, yeah. Losing that critical experience at the highest levels.
The article also mentioned a need for U.S. national labs to shift focus.
Holland argued for that, yeah. Moving from science, primarily for physics' sake, which has been hugely important, don't get me wrong, towards science more directly aimed at commercialization.
Applied science for power plants.
Exactly. making the national labs key players in actually getting fusion onto the grid, working closer with the private sector, aiming for commercial products.
And the U.S. model is drawing parallels with space exploration.
Right. The comparison is often made to the NASA COPS program, which funded SpaceX and others through milestone payments, public-private partnerships.
A model that worked well for space.
It did. But Holland's point is crucial. The initial NASA investment in SpaceX was way larger than what the U.S. government is currently putting into these fusion partnerships.
So the model might be right, but the scale of investment is maybe too small.
That's the argument. To get that same kind of transformative effect in fusion, he suggests the funding needs a significant boost, maybe 10 times what it is now.
Okay. Why is fusion seen as so strategically important beyond just the clean energy aspect?
Well, clean energy is huge, obviously, but it's also about energy security. Fusion fuel, deuterium from seawater. Lithium is abundant. It's not geographically limited like fossil fuels.
A level playing field,
Yeah.
potentially.
And it's about scientific and technological leadership. Whichever nation really cracks commercial fusion gains immense prestige and influence. Holland called it a strategic industry. Governments should want to lead, not just participate in.
A 21st century technology race with huge geopolitical implications.
Absolutely. Zero carbon, secure, high-tech energy. It's a potential game changer on so many levels.
Okay, let's try and pull all these threads together. Comparing Europe and China, what are the main takeaways on their approaches?
Europe's approach through Eurofusion is very structured, very collaborative, planned out in detail. It's anchored heavily on ITER succeeding, then moving methodically to demo. Strong international links, step-by-step R&D.
Measured, long-term, relies on ITER.
Pretty much. China, on the other hand, is characterized by, well, massive and rapidly increasing investment. They're pursuing multiple paths, big government projects like BEST, but also really encouraging this dynamic private sector.
Speed, scale, diversification.
Yeah, it shows a really strong national drive to lead, and they're willing to place bets on several horses, it seems.
And the U.S.
The U.S. is betting heavily on the public-private partnership model for commercialization, trying to leverage private innovation with government support.
like the space program model.
Right. But the big question mark hanging over it is whether the scale of that government support is enough to keep pace, especially with China's spending.
So it's clear it's not just about having the smartest scientists.
Not at all. It's about funding, strategy, industrial capacity, political will, managing huge engineering projects. It's the whole package.
Okay, this has been a really insightful deep dive. Just to quickly recap, Europe has its detailed, collaborative roadmap focused on ITER, then DEMO.
China's pouring huge resources into both big state projects and private ventures, moving really fast.
And the U.S. is using public-private partnerships, hoping to spur commercialization, but facing questions about funding levels.
If you want to dig deeper yourself, definitely check out the Eurofusion website for the full roadmap. And searching for China's fusion programs on sites like nature.com, Asia Times, maybe checking Reddit discussions, will give you more flavor.
And as you read more, maybe think about what happens globally if Europe gets fusion first, or if China does. How does that change energy markets, geopolitics?
Yeah, those are the big questions.
So we'll leave you with this thought. This whole fusion quest, it's way more than a science experiment. It's a massive strategic competition that could really define the future of sustainable energy and global leadership for the rest of this century.
Think about what a new energy superpower based on fusion might mean. It's profound.
Absolutely. Well, thank you for joining us for this exploration on the deep dive. If you found this look into the future of energy interesting, please do subscribe to Noisy Mind wherever you get your podcasts.
Yeah, give us a like, maybe share it with someone else who's into this stuff.
Your support really helps us keep bringing you these deep dives. Thanks for listening.